welcome back to Electromagnetism. Today is Electromagnetism Lecture 5, and we'll be talking about Gauss' first law. Alright, what does this mean, and how are we going to prove it? Well, this is flux, electric flux. And we can prove this via Coulomb's law. Wow, this chalk is a pain to write. So, there's the real chalk. Okay, so what does electric flux actually mean? What is flux? Well, it's always helpful to start with an analogy. So, let's say you have a bowl. And that bowl has several holes. Maybe it's a strainer or a collard or whatever they call it. And you were pouring water in it to wash like vegetables off or something, I know. And so you realize that the water is going to start flowing out of these holes at a rate dependent on how much flows in. Because of course, if the water level is low, there's going to be less holes. If the water level is high, there's going to be a lot more holes. So the flow rate is going to go up with the water level. However, paradoxically, the flux, which you might have already heard of and expected to be the same as the flow rate, does not change. How does it not change? Well, flux is actually the exact same as flow rate, except for one thing. Flow rate measures the total amount of the field, like the velocity field, that has escaped through an area. Meanwhile, flux doesn't care about the area. It's assuming you're talking about a unit area. More specifically, it's taking the amount that flows out of the area and dividing it by the area. That's the big thing about flux that separates it. So now, how do you actually find flux? Formally. Well, for the water bowl example, you might expect it to be pretty simple, right? You have a hole, you have water flowing through the hole. So the amount of water leaving through this hole per second has to be equal to what? Well, u, the velocity field, or maybe its magnitude if you consider it a vector, multiplied by the area of this hole. And that's it, right? Well, not so fast. You see, this guy implies that the whole velocity field is totally constant and always perpendicularly outward to the hole. So, for example, what happens if there's a hole in a pipe, but the water in it is flowing sideways to the hole? At the hole, the pipe velocity is still u, and the area is still a, yet none of it is flowing out because all of it is flowing down and through. So how do we remedy this? Well, we need some way to measure how close these guys are to actually going through the hole. And there's just one perfect tool for that, the dot product. That's what's going to save the day here. So, how is the dot product useful? Well, imagine we have the same hole. We take this hole, actually I should draw it in black. We take this hole, and what happens now? If the water flow velocity is directly out of the hole, perpendicular to the plane in which the hole is, then the flux out of it should be very positive. Now, if it's into the hole, the flux should be very negative because you're measuring what's leaving. Anything that's entering subtracts the total amount that's leaving. And if something's flowing sideways, like in our pipe example, then the flux should be exactly zero because nothing's flowing through. Nothing's coming in, nothing's coming out. So now the dot product seems pretty cool, but just one issue. We can't just go u dot a. The area is not a vector, it's a scalar. So what do? Well, here's what we can do. We take the area.
It is anything.
We don't have it enough.
We're gonna go this one.
No.
You have to give summary, 10 seconds.
Yeah, I will. That's just a drawing for analogy. What happens?
Actually,
Okay.
go to smartboard.
Not yet. Okay, sure. So let's pretend for a second you just have one giant water flowable source. So any water can flow through this surface, right? So now we take this surface and we cut it up into a lot of small differential areas. And we take those differential areas and cut them up even more until whatever's left is a close approximation to a plane. Any plane, of course, has an outward normal vector. The unit normal n hat. This is the outward direction. So this is directly outward. If you are perfectly aligned with this, then the entire, all of the water is going directly outward at that point. If you are partially aligned with this, then some of the water is going out, which makes the flux decrease, but it's still positive. If you're directly perpendicular, no water is coming out, like the pipe example, but none of it is going in either, so it doesn't matter. It's zero. And, of course, you can imagine what all the other cases are. So that works. We can take the flux to be the integral over area of the velocity field dot the unit vector field multiplied by dA. Okay, so this is the velocity flux. And if you want to find the electric flux, you replace the velocity field with the electric field. Now, the last part. How do we prove this using Coulomb's law? So I'm going to start on the whiteboard since we still have space. How do we prove that using Coulomb's law? Well, let's start with the case of a sphere, which is relatively simple. So we have a source charge with charge Q, and we draw a giant sphere around it. So there's a sphere around it. Let's say it has radius r. So now, what's the electric flux out of it? Assuming Q is positive, you get the electric field by Coulomb's law is 1 over 4 pi epsilon naught r squared q r hat, the radial vector. Okay, so this is shaping up to be a very hard integral, right? Well, not that hard, because you can take half of it out. But the remaining half seems a little bit formidable. So what do? Oh, wait a second, this is a sphere. So the unit vector field is just r, which means that this disappears. Well, shouldn't erase. This disappears because r dot r is r hat's magnitude, which is just 1, which makes this equal to q over 4 pi epsilon naught integral of 1 over r squared dA. But wait, this is a sphere. Over the entire surface, r squared is a constant. 1 over r squared is a constant too, which means that this is just a over r squared, a being the surface area. But wait, what's the surface area of a sphere? It's going to be 4 pi r squared, conveniently canceling out all the factors and leaving us with q over epsilon naught. And you can imagine for the general case of several particles or a solid with charge density rho, this is going to turn into rho over epsilon naught. But now they're saying, all right, that's cool and all, but that's for a sphere. And having this is nice over a sphere, you say, but Gauss's law claims that it holds generally. We can't just reduce, sure, you can take out everything else, but you can't just reduce this for a general surface where n hat is not r hat and where 1 over r squared is not always a constant. I can actually. How? Well, take any surface you want. Actually, I'll demonstrate this in 2D first because it's a little hard to see in 3D. So, I take this source particle, q plus, and it should work with a circle, but how can we know it works with a blobula? Well, here's the kicker. Let's say I take any little bit, let's say I take any little piece of this guy and call it a point P. There's always going to be a circle centered at the source charge containing the point P and almost all of its local surroundings. And in 3D, you can imagine this is a sphere, but I'm drawing it in 2D, like a cross section. And so, this would actually be tangent. Good enough. So, this circle contains P and all of its immediate surroundings. So, you can say that the theorem applies to this little section P. It's differential. But what about everything else? Well, believe it or not, I can just draw a different circle. And of course, remember that the total flux has no relation to the radius of our sphere, which means that the total flux doesn't change infinitesimally. If it did change infinitesimally, this would be broken and we would be crying right now. But because it doesn't change with radius, you can say that this circle and anything that falls on it, like this little bit right here, the theorem is valid for this guy and its immediate little surroundings, a little bit smaller than P's because it's not exactly tangent. And then you can draw another circle for anything not covered. And the great thing is, even though that circle has different radius, the flux is never going to change. The total flux is always going to be Q over epsilon naught. The laws of the universe demand that it is so. And hence, no matter what solid you pick, as long as there's a source charge with charge Q or charge density rho in the center of it, then the total electric flux out of it will be rho over epsilon naught. That's Gauss's first law. Thank you everyone for watching.